Let us see the texture mapping in computer graphics today. So this 3D rendering pipeline we have discussed, and let me recall it for you. First, we have 3D primitives, that is 3D figures, as you can say. These are in 3D modeling coordinates right now. Then we transform the model, that is model transformation is done to bring them into the world coordinate. Then the lighting is applied, which is again in 3D world coordinate, and then viewing transformation is done here. Then with the world coordinate, it is brought into the 3D viewing coordinate through projection transformation, then projection coordinate through then clipping into the 2D projection coordinate, then viewport transformation and scan conversion. So we'll see the texture mapping today. What are the textures? See, it's a wire mesh. It's a wire mesh if you only connect the points, because ultimately you only have points, 3D points. So you are connecting it either through, say, a triangle or any other, say, quadrangle. So when you are connecting them, it will just be like a simple wire mesh. But what about wire mesh? I'm saying that you have seen the football, net, the goalpost net. It is like that only. So what about making or giving it a realistic view by draping certain image? That is a texture. What you actually show on the wire mesh, that is the texture. So texture called variation in the interior of 3D polygon. This is the color variation. Okay, we'll see about that. Don't worry about that. When scan converting a polygon. So what happens here is it vary pixel colors according to the value fetched from the texture. So texture is, this is a texture. Now this is a surface. Now how this texture is transported or draped onto this surface. So this is how the final texture with the surface gives you an image. Ultimately, you have to see the image only with texture. So a texture surface, it adds visual detail to surfaces of 3D object. Right. Now this is a plain polygon model. Please observe the ceiling and the floor. The ceiling and the floor here with a surface texture. Now it is giving a more realistic view. These are the textures. So it adds visual detail to the surface of 3D objects. So see the texture mapping methods like mapping filtering and texture mapping applications also. So let's start with the texture mapping. How to map this texture? The steps in the texture mapping is, first we define this texture. As you saw, we define this texture first. So we specify mapping from texture to surface. Texture to surface mapping is done. And then we look up texture values during the scan conversion. Okay, let me tell you. This is a texture coordinate system. This is a coordinate system of texture. This is where you have to model. This is the modeling coordinate system. This is the texture. So when you drape this onto or place it, this texture coordinate system onto the modeling coordinate system, this is how it is seen in the device coordinate system, this one. Okay, so we define the structure, we specify mapping from texture to the surface, this is texture to the surface, and then we look up texture value during a scan conversion. When you are doing this scan conversion, that is, you are converting this scan converting, so what happens? A device coordinate system, which is XY, device coordinate system, this is XY, modeling coordinate system is UV, and texture coordinate system is TS. Okay, so this is how it is seen here, and this is how it will be seen here. Then we come to the 2D projection transformation. So in this 2D projection transformation under texture mapping, we transform, or there is a transformation of 2D projective transformation from the texture coordinate system, that is TS, to the device coordinate system. So what we do here, from here to here, texture coordinate system to modeling coordinate system. So texture coordinate system to this is the device coordinate system here. So ultimate aim is to take the texture and place it on the device at a particular place. So this is 2D projection transformation, that is texture coordinate system to device coordinate system. So in this texture mapping, we do the scan conversion. So what we do is interpolate texture coordinates. We interpolate the texture coordinate, that is distortion due to bilinear interpolation approximation. There is a distortion due to bilinear interpolation approximation. So we cut polygon into smaller ones. We cut the polygon into smaller ones or perspectively divide at each pixel. or perspectively divided each pixel. So this is, say, these are the texture coordinate. These are not the device coordinate or any other coordinate. These are the texture coordinate. So we try to find out the way we did in interpolation or extrapolation at that previous discussions. So these are the 2 points, and on the basis of these points, these 3 points, the texture are defined. So this is the linear interpolation of texture coordinate, and this is the corrected interpolated with perspective divide. Then we come to the filtering, texture filtering. So we must sample texture to determine color at each pixel in image. We must sample the texture such that we want to determine color at each pixel in the image. So this texture filtering, here aliasing, see this region. Aliasing is a problem. This is point sampling, this is area filtering. So we apply the texture filtering also. Okay, let us see this region. So ideally in texture filtering, we use elliptical shaped convolution filters, and but in practice we use rectangle. So this is the texture, and finally this is the screen. This is the screen representation of these elliptically shaped convolution filters. So the size of filter depends on the projective warp. So this is the see, we have in pre-filtering images MIP maps, and there are some area tables. So this is the texel or texture element. This is the texture element, and this is the picture element. So the conversion is from the texel to the pixel. So this is magnification, this is minification. What are these MIP maps? We keep textures pre-filtered at multiple resolution already. So for each pixel linearly interpolate, we try to linearly interpolate between 2 closest levels. That is, we apply the trilinear filtering. This is fast and quite easy for hardware. That is, we have already pre-filtered multiple resolution kept. Then we come to the texture mapping applications. These are all. So first is modulation texture. We map texture values to scale factor. This is the texture value. Okay, we know from here to here, we are already aware. So this is the texture value. So this is, say, we have wood texture. So we apply these two, and the combination is like this. Illumination mapping, we map texture values to the surface material parameter. So here we have various parameters, that is K, Ka, Kd, Ks. We take into account all these. So Kt will be equal to, that Kt will be nothing but this one, the TTR, that is texture function. Bump mapping, we map texture values to the perturbation. Perturbation means there is a disturbance. So we map texture values to disturbances of surface normals. These bump mapping is like this. See, this is the bump mapping. Environmental mapping, we map texture values to the environmental map. Right? This is the pixel projection onto the environment map. This is the projection reference point. So this is the pixel area. This is the surface, and this is the pixel projection onto environment map. So this is called the environmental mapping. This is image based rendering. So what we do here is we map photographic textures to provide details of the coarsely detailed polygon model. See, these are the coarsely detailed polygonal model. This is non-photorealistic rendering. So this is a very short discussion we have done on texture mapping. So if time permits, I'll tell you in detail also. I'll make one more discussion on it. Thank you so much.